Okay, so welcome to Math 150 Multivariable Calculus. This is lecture 2, and the plan for today is I want to discuss how information is presented. So this is going to be one of the big themes of the class. You're at a small liberal arts college. One of the goals we have for you is to be able to talk to people on almost any topic. And you need to figure out, how do you present information? Next, I want to talk about how one actually does calculations. And again, this is going to be extremely different for you in the 21st century than it is for me as a child of the 70s and 80s. And so to try to put things in perspective so that we can have common ground and laugh at other people, I'll actually show you some stuff from the 1940s. And so we can all agree as, ha, 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 that's what they were doing, while you're secretly thinking this about what I did when I was a kid. And then, of course, it's time to start getting to the material of the class. I want to spend 1 or 2 days just reviewing everything from Calc 1 and Calc 2 from a slightly different perspective than you've had in high school. It is extremely easy for a math teacher to cut corners and make you feel like you've learned something when you haven't. There's a lot of things that look right, but you have to work hard to put it on a rigorous foundation. I am not going to require you to do advanced proofs on exams or on homeworks. If you stay with math, if you stay with physics, if you stay with some of these sciences, eventually you will have to start doing that. I want you to start seeing it now so that when you start getting into it later, if you get to it later, it's not so much as a shell shock. And if you ever want to try to, your hand at trying to prove some of these, I'm happy to give you some problems to look at and happy to talk to you. But I want to show you mathematics is nothing if we can't make it rigorous. The reason that something is true is not because I said so, but because I can give you a demonstration as to why it is true. Hello? Hello? Yes? Okay, it doesn't show you in the waiting room right now. Okay, try. All right, so try to join again. And this is why, as I said, keeping the cell phone. All right, so for those of you who are successfully in Zoom land right now, I'm actually going to make one of you a co-host. So I've just let them in. If you see someone else coming in, as long as they're not named Zoom Bomber 2000 or something like that, please let them in. Zoom Bomber 100 is okay. Just seeing who's listening. Okay. So going back, so it's very easy to think you've proven something when you haven't. Mathematics is not true here because I'm a professor at Williams, I have degrees from Yale and Princeton, doesn't matter. It's true because I can convince you it's true by going through a chain of arguments where we agree on the assumptions, we agree on the rules of logic. I know there's at least one person here who comes from a family with a philosophy background. So with you, we can argue as to where do we want to start our assumptions. And if you choose different assumptions, you can get to different results. And for a lot of things, for trying to find statistics and metrics, depending on what you choose, you can easily get to different answers as to what is the best solution, depending on how you measure things. All right, so we'll start going through in terms of presenting information. So this is something I took a picture of recently. Might be a little bit hard to read this, so I'm going to zoom in. Anybody want to take a guess as to what this is? So I'll give you a few seconds to look. Whenever you see information, you always want to figure out what is it, what's being displayed. So this is one of the more interesting pieces of paper from the 20th century. Can anybody tell me at least when it's from? Yes. 1917. Not 1917. That's the age. That's I think when the person was born. 1945, August 1945. What is this? Flight record. Anybody want to guess what? So there was a flight on August 6th, 24th, and 26th. Anybody have any thoughts as to which mission? This is from the first atomic bomb drop. So I was at the World War II Museum. This was the flight record from Colonel Paul Tibbets, who was in command of that mission. Very matter of fact. This is a great topic, not for in class, but if people want to talk about it afterwards, about ethics and the applications of math and science. And these are very complicated issues. If anybody wants to talk about stuff like this, happy to do so. It's also a nice way to introduce an interesting math concept. How many of you have either heard of 6 degrees of separation or the Kevin Bacon game? So have you done a movie with someone who's done a movie with someone who's done a movie with Kevin Bacon? So I am 1 degree of separation from the person who flew the mission. So I've shaken hands with somebody who's shaken hands with him. It's an interesting question to think, what does it take to connect you with someone? What is a good metric to think of trying to figure out how connected you are? This doesn't mean I know somebody well enough that I can call up and get to this person. And so when we're trying to figure out what do we want to study, a lot of times in calculus classes, you just say, we're going to look at this function. Okay, why do we choose to look at this function? I want you to be thinking about what do we want to study? What's a good metric of connectivity? We could have the connection function. And here's the handshake connection function. Have I shaken hands with someone who's shaken hands? When you get a little bit older, around 21, you might find out there's this thing called alcohol. And then you can start asking, have you drunk with someone who's drunk with someone who's, and have the drinking connective number. You could have the telephone connecting number. Do you have the telephone number of someone who has the telephone number of someone? So part of this is I really want you to be thinking about what we're studying and why. What functions are we looking at? Do these functions actually describe what we want them to do? All right, so I said we could make fun of the 1940s together. This was a computer from the 1940s. See, it says computer on it, so it must be a computer. A little bit of it different than what we're doing now. So again, I've mentioned numerous times, you are going to do calculus differently than I learned it because you have all of these online resources. What was going on back then is that it says the true airspeed is the aircraft speed in relation to the ground due to the influence of air pressure at various altitudes. The indicated airspeed the pilot sees on his instruments is different than the true airspeed. For the sake of accuracy, bombardiers had to enter the aircraft speed in relation to the ground into the bomb site. This circular slide rule computer would quickly calculate true airspeed and is still used by pilots today. So a very simple device to save you from having to do laborious calculations. Quickly spin it around, put it there, and it highlights what the conversion factors should be. This is one of the big themes you want to think about. What calculations are you doing again and again in your life, and what can you do to make it easier? If you're going to be learning how to use integration to solve problems, to use differentiation to solve problems, you want to learn how to use something like Mathematica, Wolfram Online, Dymos, all these different packages so you can do these calculations quickly. So you can check the work you're doing by hand. All right. Last one I wanted to do was they were trying to display in an interesting manner the relative strengths of different countries at the start of World War II. And so they have the armies of Japan, the Empire of Japan, the United States, and Nazi Germany. And so they did it visually by drawing, by putting little soldiers for everything. But they also had some text. I'm just trying to minimize the images over here, but the mouse never seems to work well. Okay. And so, again, it's trying to figure out how do you present information in such a way that it makes sense. When you see the numbers, 850, 335, 3.1 million, how effective is that to you in describing what's going on? Here's a way of trying to do it visually to just get a sense of roughly how do those numbers compare. The text says the US Army was comparable in size to much smaller states like Bulgaria, Portugal, and Romania. Is there anybody from class from any of those 3 nations? Okay, so when you hear those nations, you really don't think military superpower, right? And trying to put in context, we can give you the size of the US Army relative to these other countries, the big players, Japan and Germany. But when you have the US in the same sentence as Bulgaria, Portugal, and Romania, I think it really drives home the point of the relative sizes. When you are using the math that you're learning, hopefully you'll be using this to convey to people, to try to convince people about something. Really think about how do you want to present the information. And if this is a topic that interests you, there are some books you can read about how do you actually present information. And I'm happy to share that with you so that you can have good, effective conversations. All right. So what I want to do now is start the review of calculus. So we talked last time about the standard definition of the derivative. And that definition was f prime of x is the limit. How do I do that? I'm going to change, instead of doing f prime at x, I'll do f prime at the point A. So f prime at A is the limit as h goes to 0 of f of a plus h minus f of a over h. And we talked about, if we draw the function, and here is our point A, what we can do is we can do the secant line that connects them, and here would be a plus h, and we could take the limit as h goes to 0, and then that would give us the instantaneous change of what would be going on over here. So this is the definition everybody knows and loves. Nobody ever wants to compute with this. The whole point of Calc 1 is to derive rules of differentiation based on this, so we don't have to go back to the definition of the derivative. I can, of course, rewrite this in a lot of different ways. One way of rewriting this is the limit. Oops, I lost this. So this is the same as the limit as x goes to a of f of x minus f of a over x minus a. Why is that true? Why is that the same as the previous one? How can I view them as the same?
You're basically switching x for a plus h.
Good. Just let x equal a plus h. As h goes to 0, x goes to a, and vice versa. So really, there's no difference between these two. Now, I claim this is the same as the limit as x goes to a of f of x minus f of a minus f prime of a x minus a over x minus a equals 0. And the reason this is the same, to make sure I always walk with this so that the audio is recording, the reason this is the same is, well, just bring f prime of a inside the limit, because f prime of a is a constant. It has no change as x goes to a, because it's just a constant. And then I do one of the most common things in mathematics, nothing. There are two good ways to do nothing in mathematics. What are the two good ways to do nothing? So this has one of the two ways of doing nothing. How did I get the f prime of a where it is? What nothing did I do? You might have seen this when you did rationalizing expressions in high school. If you have 3 over square root of 7, what would you do? Yes. I multiply with the denominator. So I multiply by the denominator with the denominator. So I'm multiplying by 1. You don't change a value when you multiply by 1. When we take the limit as x goes to a, x is never equal to a in the limit. It's getting closer and closer to a, but is never equal. So we multiplied by 1. Okay, as x goes to a, but is never a. So the other thing is, instead of multiplying by 1, what's the other way to do nothing in mathematics? You can multiply by 1. What else could you do? Add 0. So those are the two ways to do nothing. And so really, these two expressions are the same. The last one is the one that's going to generalize to multivariable calculus. When we ask, what does it mean for a function to be differentiable with several variables? This is the expression that's going to do well. The limit as x goes to a of f of x minus the tangent line approximation divided by x minus a goes to 0. And so if you think about it, the whole idea of the tangent line approximation is, look, If I tell you where I am and I tell you my instantaneous speed, I should know where I'm going to be a small amount of time later. If I'm driving from Boston to DC and I'm somewhere in Connecticut and I tell you I'm traveling at 50 miles per hour, because of course I don't speed, do you know exactly where I'll be 1/1000th of a second later? Yes. Do you know where I'm going to be 1 hour later? No, that's a long enough time that maybe I now hit the New York City traffic. Maybe it's been a bad day. But in a very short period of time, I know where I'm going to be. We talked in the first class about how numbers are relative. Is $10 million a lot for us? Yes. Is it a lot for Elon Musk? No. When we're looking at how good is the tangent line approximation, well, I expect the tangent line, view this as f of a is where I am, f prime of a is my instantaneous speed, x minus a is my elapsed time. We're basically saying the gold line does a really good job of approximating the curve for small periods of time. Well, of course. I mean, hell, just use f of a, and that's going to be a good approximation, right? In a small amount of time, I really don't move. Okay. Then the next best thing is, well, let's try to incorporate a little bit of, I know how fast I'm moving, so I can figure out where I should be a short time later. That's going to be the f prime of a times x minus a. Well, I expected this is going to be very close. It was already close with just f of a. So we always do things relative. So numbers are relative. So the error is small relative to the elapsed time, x minus a. So not only is it a small error, it's small relative to x minus a. It's so small that even when we divide by x minus a, it's a small number. Okay? So this is the notion of the derivative. This is the most important idea in calculus. And over here, we also have this beautiful idea of this tangent line approximation. And that's what's going to generalize when we talk about higher dimensions. What do you think a line is going to become when we go to a function of 2 variables? What would you guess? What do you think a line becomes? Any thoughts? What would be the next object as we go up a dimension from a line? What do you think we would get? A plane. And if we go up another dimension, we go to a hyperplane. And hyperplane is this catch-all for all the stuff that comes from that point onward. So we replace saying that locally the function is given by a line with locally the function is given by a plane. And for small amounts, it's going to be fine. In one dimension, there's really not that many ways to approach the point A. If I want to approach the point A, there's really only 2 ways to approach A. What are the 2 ways to approach A? So how could I approach A? Yeah, left and right. We will see later that in high dimensions, life is a lot more interesting, right? As I'm walking in the front of the blackboard, I feel like I'm confined to one dimension, but I could start lecturing like this, except of course with college COVID policies, I'm not sure if I'm allowed to do that. So I will keep myself for the most part early in the semester confined to the line over here. But as we relax the COVID policies, as the semester continues, then I can start giving a multidimensional lecture. Right now, staying just in a line, it's boring for me, right? There's not that much flexibility. It also means it's not a big deal to be differentiable in one variable. There's really only 2 possible paths. We'll start to see that there's a lot more possible paths in higher dimensions. Okay, so the next thing is to start proving differentiation results. So I'm going to give a quick test. So here's the function f of x, and I want to know what is f prime of x. So x cubed, x to the 3/2, x to the square root of 2. Can someone tell me what is the derivative of x cubed? 3x squared, excellent. What's the derivative of x to the 3/2? 3/2 x to the 1/2, x to the root 2. Yes?
Root 2x square root minus 1 of 2. Or square root of 2 minus 1.
Square root of 2 minus 1. And more generally, if I give you x to the r as a Bostonian. Yes. Did you prove this in school? So how did you prove the first one? Okay. Anybody remember how you proved this? So for the first one, you might have done the limit as h goes to 0, x plus h cubed minus x cubed over h, and use Pascal or the binomial theorem. And that's going to be x plus y to the n is the sum, k goes from 0 to n, of n choose k, x to the n, I'm sorry, x to the n minus k, y to the k, where n choose k is n factorial over k factorial, n minus k factorial. It's the number of ways of choosing k objects from n when order doesn't matter. You might have seen these in Pascal's triangle, where each number is the sum of the number above to the left plus above to the right. And there's lots of ways to show this. This is an extremely useful result. And we would then get x plus h cubed would be x cubed plus 3 x squared h plus crap with at least h squared. That's a technical term. Okay. We now subtract from both sides in x cubed. And what do we get? We'll get, our numerator. And over here, we'll get 3x squared h plus crap h squared and higher. Then if we divide by h, you see this has h or higher. Because everything here had at least an h squared, when I divide by h, it's going to still have at least an h. So when I take the limit as h goes to 0, it's going to vanish, and I'm going to get my 3x squared. And that's how we prove x cubed. With a little bit more work, I can do x to the 4th, x to the 5th, and all this. Can anybody tell me what's the derivative of x to the 24601? So what's the derivative of x to the 24601? Okay, good. And I'm assuming you've never done that derivative before in your life, but you were able to do it immediately right now, correct? Yes, right? That's the power of something like this, is we isolate the rule. We have the rule x to the r is r, x to the r minus 1. Anybody know why I chose 24601? Yes. That's Jean Valjean's number. Yes, very good. So email me for cultural extra credit, right? If you can email me in French, you get even more. Now, we've got to be very careful that we're actually proving something. That's how we prove the derivative of x to a positive integer. What about x to the 3/2? You all got it right. How many of you proved the derivative of x to the 3/2 is 3/2 x to the 1/2? A little scary. You're in college now. So how did you do this in high school? So later today, think about what the hell did they do in high school? How did you get this? So we can't just use Pascal's triangle or the binomial theorem that only works when we have something to an integer. There's a combinatorial interpretation for what's going on. I'll do the simpler case. Let's see. So let's do the simple case. Let's do f of x is x to the 1/2. then I can do f prime of x is the limit as h goes to 0 of x plus h to the 1/2 minus x to the 1/2 over h. I'm going to do nothing. Can anybody think of a good way to multiply by 1? What could I multiply by 1 that would be good here? Any thoughts? So I could do h over h, but if I do h over h, the h doesn't really help me, unfortunately. So trying to look at the denominator is not going to help. It's not a bad thing to try, but that h is not going to do anything to the numerator. I want to fix either the numerator or the denominator. You've had a focus before of always making the denominators nice. Can you multiply by something and make the numerator nice? I'm sorry? So if I just do x plus h, that's not going to interface nicely with the square roots. X plus h to the 1/2, but I need a little bit more. Plus x to the 1/2. And then I can divide by itself. And if I do that, I now get the limit as h goes to 0 of x plus h minus x over h, x plus h to the 1/2 minus x to the 1, I'm sorry, plus x to the 1/2. So this is going to be the limit as h goes to 0. Oh, nice. The numerator becomes h, which cancels down below with 1 over x plus h to the 1/2 plus x to the 1/2. What does the denominator go to as h goes to 0? It goes to 2x to the 1/2. So it's 1 over 2x to the 1/2, or 1/2 x to the negative 1/2. And there's our answer. Now the question is, well, what if I give you x to the 7/13? Can you still do something like this and make it work like that? It turns out there's a better way. Let's let g of x be f of x to the q if f of x equals x to the p over q. I'm going to do all rational things. So I'm assuming now that you've done the power rule, which is a special case of the chain rule. If I have f of g of x, the derivative is f prime at g of x times g prime of x. If I give you f of x to an integer, n, its derivative is n f of x to the n minus 1 f prime of x. That only works if n is a positive integer. Here, okay, q is a positive integer. Now we get g prime of x is going to be q f of x to the q minus 1 f prime of x. Right? So f prime of x is going to be g prime of x divided by q f of x to the q minus 1. But g of x is f of x to the q. What does g of x equal? What would g of x equal? I'm sorry? Well, g of x is f of x to the q. F of x is x to the p over q. So what would g of x be? So I'm raising x to the p over q to the qth power. So you've got to remember, it's just x to the p. This is the laws of exponents. You know, if I take something to the 3/5 power and then raise it to the 5th power, it's the same as cubing it. If I take something to the 3/7 power and then raise it to the 7th power, it's the same as just cubing it. Well, okay, well, g of x is x to the p. I know its derivative. It's just going to be p x to the p minus 1. And then the denominator is q, and then f of x to the q minus 1. That's going to be x to the p times q minus 1 over q. now do algebra, and you see we get f prime of x is p over q times x to the p over q minus 1. So I'll let you do the rest of the algebra because I want to review more calculus. So I strongly urge you to go through. This is a way to just make sure that you're comfortable with the algebra that we need. But the idea is to prove the derivative. We prove it in the special case first when I have f of x to an integer power. Once we have it to an integer power, we can then get it to a more general case. One avenue is potentially to do some really clever multiplications by 1. This worked for x to the 1/2. Can I get this to work in general? And how bad will the algebra be? The whole idea of calculus is we have all these rules of differentiation. You never want to keep doing things from scratch. You never want to go back to the definition of the derivative, roll up your sleeves and do the calculation. You want to just move on. And so by isolating these rules, I now use the power rule. And I said, well, look, I've got f of x is x to the p over q. I don't really know what that is, but if I raise it to the qth power, I have a nice function. And I know how to take the derivative of that function. I know how to take the derivative of x to the p. All right, let's move on. Technically, you might have to be a little bit concerned about, well, what if p is a negative number? So I'm going to assume we've already done the quotient rule. So if I give you x to the -3, I can write that as 1 over x cubed and use the quotient rule. All right, so now we have the last one. We now have, say, g of x is x to the root 2. What the hell does it mean to take something to the root 2th power? What does it mean to square x? What does that mean? What's x squared? Yes. Multiply x by itself. What about cubing x? X times x times x. Okay, I can understand that. What does it mean to take x to the 1/2 power? So I now want x to the 1/2. What would that mean? Yes. So what does it mean to multiply number now? So what does that mean? Okay, what does that mean? Excellent. Find a number y such that y times y equals x. Ah, okay, good. That's now bringing me back to the situation of doing shit I know, right? I can multiply something by itself. Okay, if my choice of y is too small, if y times y is less than x, increase my guess for y. If y times y is too large, decrease. Okay, that's not so bad. If I give you x to the 3/5, I'm looking for y such that y times y times y times y times y 5 times is x times x times x. I'm back to integer multiplications. I can do that. What does it mean to raise something to the root 2th power? One possibility is to say, well, let me start looking at the infinite decimal expansion for root 2. So root 2 is about 1.414. So I could first calculate x to the 1st power, then x to the 1.4 power, then x to the 1.41 power, then x to the 1.414 power, and so on, and hope that this converges. The other approach is I can say, let's write this as e to the f of x. And let's try to find a way of writing this as an exponent. So if this is true, if I take the natural log of both sides, I will be kind today and use ln for the natural log, but in college we actually use log for the natural log. No one does serious scientific studies with logarithms base 10. It's the natural log that's nice. And the reason is the derivative of the natural log is what? Remember, is the derivative of the natural log 1 over x. If you have the log base b, then there's an extra factor of the natural log of b that comes into play. What's the derivative of e to the x? E to the x. If you have b to the x, then there's a natural log of b that comes into play with the derivative. It makes things nicer. It's similar to how we use radians and not degrees for trig, because now the derivative of cosine is minus sine, the derivative of sine is cosine. If you don't use radians, you have conversion factors. So if I want to solve this, I get the natural log of x to the root 2 is the natural log of e to the f of x. So I would get root 2 natural log of x is equal to f of x natural log of e. What's the natural log of e? It's just one. Yep. So now, so g of x is e to the root 2 natural log of x. Thus, g prime of x is e to the root 2 natural log of x times, by the chain rule, the derivative of root 2 natural log of x. What's the derivative of root 2 natural log of x? Well, the root 2 is just going to be a root 2, constant rule, and the derivative of natural log is 1 over x. Then e to the root 2 natural log of x, well, that was the same as x to the root 2, so we get root 2 x to the root 2 minus 1. So to actually figure out what is the derivative of x to the root 2, we're really using the chain rule, and we're using what the derivative of e to the x is, and we're using what the derivative of the natural log of x is. This case actually covers all the other stuff. I can replace root 2 with anything here, and that just changes the number there. So again, it's really important to get a sense of what are the results and how do we get to them. Okay, I'm not going to hold you responsible for everything, but this lesson should serve as a warning to you about being very careful when someone tells you something. You know, when you did your rules of differentiation in high school, or maybe even in college, they may have glossed over points like this. Most of the time it's okay. We've got mathematicians working on this, you know, behind the scenes to make sure everything is okay. But every now and then something is missed. Oh, Jack, put things in the wrong order? No, okay. So I want to quickly talk about the meaning of the derivative. So I will go back to f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. And again, let's say, you know, here is my function. Here is my point x. And here, whoops. And here is what's going on at this point. So the first derivative is the slope of the tangent line. So if f prime of x is greater than 0, what can you say about the function? So then f is increasing to the right and decreasing to the left. And if you look at what's going on, if the first derivative is positive, if I move to the right and I put myself here at x plus h, then h is positive, so the denominator is positive. If the first derivative is positive, then what must be true about the numerator? It has to be positive. Now, my function could eventually maybe dip down. So if I go really far out, the numerator could be negative. But if I'm very close to x, if the first derivative is positive, then f of x plus h has to be larger than f of x. So locally, if the first derivative is positive, my function is increasing. If f prime of x is less than 0, then f is decreasing to the right and increasing to the left. So the interesting case is what? Yeah, so what does it mean if the first derivative is 0? So a little bit careful. Let's say I give you f of x is x cubed. What's f prime of x? 3x squared. What's f double prime of x? 6x. So if f prime of x equals 0, we say x is a critical point. This is a candidate for a local maximum. So the function I just gave you over here, if I were to plot it, it would look something like this. So it does not have a maximum or a minimum at x equals 0. What do you think is going on? What do you think is causing this change, this difficulty? So it doesn't have a maximum minimum. Anybody have any guesses as to what's special about this function? This was a very cooked up example. Yes. Okay, yeah. Right. So another way of looking at this is the second derivative is 0 at 0. And so if you go a little bit to the left, it's positive. If you go a little bit to the right, the second derivative is positive. This is a strange situation where basically it has a positive acceleration, stops instantaneously, and then resumes its positive acceleration. So the fact that the second derivative is 0, that's what changes things. If just the first derivative is 0, then you will have a local maximum minimum. It's the fact that the first derivative and the second derivative are both vanishing that's causing some difficulty here. But again, a lot of times when we're trying to find key points, we just want to have a set of candidates to check. And this is one of the biggest applications of calculus, is trying to optimize things. I have some problem and I want to know what's the best choice. So who here are my econ perspectives? Okay, one, maybe two. Okay, so a lot of times in economics, you do marginal cost equals marginal utility. You want to figure out how much of this product do I keep building? Well, a lot of times when you're building something, you have a lot of fixed costs. You have the building that you've bought or rented. You have the supplies. But then you sometimes have additional marginal costs. The more products I buy, maybe the more raw input I have. But I might not need to hire additional labor in certain regimes. And then you start to look at how much more money am I going to make by producing things? If you have too much stuff on the market, you're going to flood the market. You may not be able to sell them all. And so you keep producing until you get to this indifference point. The cost of producing one additional item equals the revenue I get from that one additional item. Okay. As long as I'm gaining more utility from making more items, I'll keep making more items. So this is a great application of calculus. All right. What I want to do now is talk a little bit about some of the key theorems. So I'm not going to go through all the details of the proof here. The details I'm posting in the slide. This is from a review appendix from a book I wrote with a colleague years ago. It's the intermediate value theorem, the IVT. This is the first of the duh theorems. What it basically says is there are no transporters in the real world. If you start off 4 miles from home and end 9 miles from home, what must be true if you walk continuously? You start 4 miles from home, you end 9 miles from home. What must be true? Yes. Okay, but be more specific. Yes. At some point you were 5 miles from home. At some point you were 2 pi miles from home. Any value between 4 and 9 you hit at some point in your travels. You might have been 10 miles away from home at one point, and then you realize, oh crap, we forgot the gift, and we have to go back home and start to get it. You might have actually realized that as soon as you left and gotten closer. But we know it's a certainty that you must at some point in time have been every value between. And so the way we write this in mathematical speech is let f be a continuous function on the interval ab. For all big C between f of a and f of b, there's a little c in the closed interval ab such that f of little c equals big C. Anybody ever watch Star Trek? So the reason they invented transporters in Star Trek is they did not have much money in the 1960s when they were making Star Trek. They were on a shoestring budget. They had to conserve every cent they could. And so for the pilot episode, they didn't have money to have a shuttle go from the Enterprise down to the planet. And so, well, what if we just put a little button here and we push the button and go, and now all of a sudden they're on the planet. How much will that cost? We can afford that. And that's where the transporters came from. Any potential physics majors here? They have what's called Heisenberg compensators to compensate for the uncertainty principle. That's the physics behind it. Right? The intermediate value theorem is a really obvious theorem. The next one is our second pretty obvious theorem. So the mean value theorem says let f be differentiable. So it turns out if you're differentiable, you're automatically continuous. So let it be differentiable on an interval, then there's some point in that interval where f of b minus f of a is f prime of c times b minus a. The way you can view this is you can write this as f prime of c equals f of b minus f of a over b minus a, or at point c, the instantaneous speed equals the average speed. And just to write it a little bit more graphically, if I give you something like this, and here's my function, here's a, here's b, and I can draw the line over here, then I have to have at least one point where my instantaneous speed equals my average speed. So I'm going to give you the obvious proof of this. Let's say you're always traveling at 50 miles an hour. At some point in time, are you traveling at 50 miles an hour? You should be laughing, right? I'm going on the Tonight Show later this week. I got to make sure everything is working, right? Of course, if you're always traveling at 50 miles per hour, then at some point in time, you're traveling at 50. In fact, every point in time. What if I am always traveling faster than 50 miles per hour? Could my average speed be 50? No one is that good. You can't be traveling faster than 50 miles per hour for the entire region of time and have your average be 50. Similarly, you can't be traveling less than 50 miles per hour and have your average be 50. So there are two cases. Either I'm always traveling at 50 and then any point in time works, or at some point in time, I must be traveling faster than 50 miles per hour, and what must also be true. At some point in time, I must be traveling slower than 50. And now I use the intermediate value theorem applied to which function? So which function do I apply the intermediate value theorem to? I know at some point in time, f prime is greater than 50. I know at another point in time, f prime is less than 50. What do I apply the intermediate value theorem to? Which function? So I'm trying to conclude that there's some point in time where my instantaneous speed is 50. I know at some point in time, f prime is greater than 50. I know at some point in time, f prime is less than 50. So which function should I apply the intermediate value theorem to? Yes. Well, so do I need to use f and f prime, or just f prime? I know there's some time when f prime is greater than 50. I know there's some time when f prime is less than 50. I want to show that there's some time when I'm traveling at 50. Just f prime. I don't need to apply the intermediate value theorem to f. I'm just applying the intermediate value theorem to f prime. And so that's the nice, intuitive proof as to why the intermediate value theorem implies the mean value theorem. I go through a longer exercise over here. This illustrates a really nice idea in mathematics. Take whatever you're given and reduce to something simpler. And so Rolle's theorem, which you might have seen in high school, is it's enough to do this in the special case when f of a equals f of b equals 0. And you're basically then just saying, in this special case, you just have to prove that at some point in time, you're not moving. So I'm not going to go through and do the algebra of that, but just so that it's showing the slides in the video, this would be the argument. So this is a lot of the key ideas of Calc 1. Is what does the derivative mean? Here are the two big rules. What's the definition of the derivative? What does it mean for a function to be differentiable? How do we calculate derivatives of simple functions? More complicated functions, the calculations will be a little bit harder. We have the rules of differentiation, which I'll talk a little bit about next time. I can't give you any differentiation problem that you can't solve. I can easily give you problems you won't like. That's not a problem. I can't stump you. Integration is completely different. I can easily give you painful integration problems that you can't solve. All right, it is now 9:50. This is a good place to stop. Have a good rest of the day.